Should be working now. Hi, everyone. This is the second... The police are outside my window. How fun. This is the second one. So this is the April multiple choice examination. Now, not all of the questions in this are valid for our test, but I'm going to cover them anyways, just to make sure everyone's clear on whatever questions they're doing. Anyway, let's get started. So, for number one, you've got a production function here, fkl. Okay, so you've got f of k and l is equal to kl. Okay, and you want to determine which is false, essentially. So you've got, is the production function concave? Is it negatively sloped? Are the isoquants negatively sloped? Pardon me. Are the isoquants convex? Is the production function quasi-concave? And are the returns to scale increasing? Okay. I mean, right out the gate, let's start working on our first one. So for a production function to be concave, okay, we need to look at our rules for concavity. So it is concave if it is negative semi-definite, okay? That's what we're talking about. Concave means negative semi-definite, okay? So to find that, we're going to derive by k here, partially by k, which gives you L, and then partially by L, which gives you k. Then moving on, you get 0, 0, 0, and 0. Now, this one, is this negative semi-definite or is it positive semi-definite? Here's the thing, okay? It's not concave, and it's not convex, okay? A zero Hessian matrix is essentially a positive semi-definite and a negative semi-definite at the same time. Therefore, we cannot definitively say if it's concave or convex, because it's technically neither, okay? It's technically not any of those two, okay? So it's the false, okay? But we can say that the isoquants are convex. There's the important thing about the isoquants is that they are distinct from the actual function itself. So, for example, if you have a function like this, the isoquants are still going to be convex, even if the function itself is not necessarily concave or convex. And also, the production function is quasi-concave, I believe. Yeah. To be honest, this one's a bit confusing to me as well. There is some work on this. I think if you look at pages 359 to 360, there's some detail there, but it's quite tricky to like this. All right. Quasi-concave functions. Yeah. So you would determine all this sort of stuff here. So you would have, so for example, a quasi-concave function doesn't necessarily have to be concave. This is why D can still be correct, okay? But every concave function must be quasi-concave. So D must be correct even if A is incorrect. But if D was incorrect, then A would be incorrect. So we know that D wouldn't be incorrect in this case. Okay. Now for number two, we've got a Lagrange multiplier problem. Okay, we've got this problem here. So let's phrase this. As you can see here, it's already kind of phrased for us quite neatly. So I'm just going to write this out here in bigger letters, just so everyone's clear. Then plus bz, b lambda. Okay, now, simply put, we're going to start by partially deriving each of these. So partially deriving this function with respect to x, you get 4x minus lambda. Doing the same for y, you get 4y minus lambda. But for z, you can see that it has no 2 coefficient. So instead, we're going to get 2z minus lambda. And these all equal 0, as we all know. So you will get x is equal to lambda over 4, y is equal to lambda over 4, and z is equal to lambda over 2. Now, if we reinsert these back into our constraint, we would get lambda over 4 plus lambda over 4 plus lambda over 2 equals b. Now, what do these sum to? Well, a quarter plus a quarter is a half, and then a half plus a half is a whole, right? So lambda is equal to b. Therefore, the answer there is D, because D states that lambda is b at the optimum. So we've got that. Okay. Number 3 is not one we are covering. It is long run and short run cost. So we're not covering that yet. That's in envelope theorems. That'll be coming up later. And then we're also given a cost function for a firm. Now conditional input demand functions, or CIDFs. That's not a D, that's a P. So CIDFs are essentially partial derivatives of the original function. Here, it's stating which one of the following is a conditional input demand function of input 1. We can see that input 1 is represented by W1, so we're just going to partially derive by W1. So our original function here is K W1A, W2, 1 minus A, and then YB. Okay, partially deriving relative to W1, you get K A, W, A minus 1, 1, W2, 1 minus A, and then WB. Which one is that? That is C. Okay, so the answer there is C. There you go. All right. Now, for 5. This one is a little trickier. Let's be honest, it took me a while as well. And I'm not entirely sure why. Now, if you were to actually do the Hessian matrix for this, you would find that first of all, the gradient vector, deriving the lins there, you would get 1 over x1 plus x2, and then 1 over x2 minus 3. And then going to the Hessian matrix, you would actually find that it would be negative 1 bracket x1 plus 2 squared. And then in the bottom diagonal, you'd get x2 plus minus 3, and then the rest would be 0. Now in this case, you can see that the diagonal entries are always negative. And you can also see that the derivative, not the derivative, there's so many similar words. Derivative, determinant, discriminant, they're all very similar. It's just very hard to keep track of them all. But you get x1 plus 2 squared and x minus 3 squared. Okay, that's the derivative. That's the determinant. And as you can see, this determinant is always going to be non-negative. Okay, so if the determinant is always non-negative and the diagonal entries are non-positive, then let's look at our guideline here. So the diagonal entries are non-positive and the determinant is non-negative. This means it is a negative semi-definite. But a negative semi-definite, if we look here, okay, a negative semi-definite gives a strictly concave function. So this function must be concave. So you would think that the indifference curve being convex would be incorrect. Not so. As a matter of fact, this one is incorrect. Okay, meets at the x1 axis. If we were to actually plot this graph out, in fact, I can do this. Let me show you. So say I was to plot this graph out. So let's just make this equal to 3. And then we do ln x plus 2, ln. I'm just using x as x1 and y as x2 here, just for simplicity of just showing the point. As you can sort of see here, if I zoom out, yeah. So you can sort of see the indifference curve here. It intersects the y-axis or the x2 axis, but it doesn't intersect the x1 axis. It lies above there, which is because you've got that asymptote at x2 equals 3. So it can't go further down, which means it can't satisfy a b. The indifference curves being convex is basically that if your utility function is concave, then your indifference curves correspondingly will be convex. I think that's true. I may have to look up that. Again, look at these 359 to 360 just to confirm that. Okay, moving on. The problem 6 maximizes, you've got fxy relative to that. Now, yeah, you've got the standard Lagrangian. Which of the following is not true of the optimum? So, what cannot be ever true when it comes to the optimum? Well, if we sort of think about it, if we want to maximize something, we can never really have a value of lambda lower than 0, because that doesn't make really much logical sense. As you can sort of see here, the top two are perfectly valid. They work for the partial derivatives of the functions, and they would work for this fxy minus lambda gxy. The partial derivatives then work. You would also get lambda of g of x equaling 0. That is just the standard thing you do. Now, the lambda being above or equal to 0 in D also works, but E doesn't. Okay, because if we have a lambda under 0, then it essentially shows that it cannot be maximized in a way. It's going to be minimized. Okay, hopefully that works. Now, this time we're going to be doing 7 here. We're going to find the minimum value. So using the standard Lagrangian format, we're going to write out our first function. And subject to minus 3 lambda x minus 4 lambda y. And we're just going to omit the 8 because we know it gets cancelled out usually. Okay, this gives you dl dx of, well, deriving this, you get, put the 2 in front and the derivative inside is just 1. So it's just 2x minus 1, so it's 2x minus 2. But then deriving this, you've got the minus 3 lambda over there. Okay. You'll also get, and this is equaling, I think that's right, yeah? Yeah, that is right. Okay, so this is equaling 0. And then for the partial derivative relative to y, you've got a similar thing, but it's going to be minus 4 lambda. Okay, in this case, you get, I believe that is, lambda is equal to 2x over 2, 3, I believe. Just wondering if I actually did things right. I've got my workings out here. They're in a waste paper bin. It's not entirely professional. No, that should work. Yeah, oh no, sorry, we've got to rearrange for x. Such an idiot. Okay, rearranging for x, you sort of move the lambda and the 2 over to the other side, and then you divide by 2. Gives you 3 lambda plus 2 over 2. And then y over here, you're moving these two over to the these two over to the right side, which gives you 4 lambda plus 2, and over 2, that gives you 2 lambda plus 1. Okay. Basically reinserting these into our budget constraint. We're given that, so you're given 3 lambda plus 2 over 2. And then you're given plus 4, 2 lambda plus 1, which is smaller than or equal to 8. If you times by 3, you get 9 lambda over 2, and then you get, I believe that's 2 over 2, so that's 1, times the 3 gets plus 3. Then you've got the plus 8 lambda plus 4 over here, which is less than or equal to 1. Subtracting out the 3 and the 4, you get, sorry, that was 8 originally. Subtracting out the 3 and the 4, you then get 1. And then adding these up, you inevitably get 25 lambda over 2, I believe, smaller than or equal to 1, which gives you inevitably lambda must be smaller than or equal to 2 over 25. So this is a lot of work. So if you use this lambda in the equation, you are then given basically that like anything below this is minimized. But the thing is, this isn't actually required. Now I've seen it. Oh god. Okay. Oh god, this is so stupid. Okay, just have a look at that function. Okay. Just looking at it. Okay. When the budget constraint essentially says you have to be under 8, you can literally just insert points here, and it would work. Okay. So, inserting 0, 0, you get negative 1 squared plus negative 1 squared, which is 2. Not perfect, but it is still under our budget constraint, right? What if I insert 1 and 1? Well, it's 1 minus 1 squared plus 1 minus 1 squared, which gives you 0, which is pretty much as low as you can pretty much get at this point with a square. And that does fit under our budget constraint because it's 3 plus 4, which is 7, which is under 8. So that works. Any other thing would literally just give you 0 plus 1 or 1 plus 0. And it's not E, none of the above. Because there's essentially no other possibility here to get lower than 0. So it's B. That's essentially it. You don't need to do the long Lagrangian for this, which is a little annoying. Sometimes you don't need to, do everything you need to do just to get an answer. Sometimes it's right in front of you. Right, which is a good approximation if for ln of 1 plus x, if the magnitude of x is small. Again, let's go back to the graph. Again, I would recommend you guys have one of these graphing calculators because they are really useful. Always in a good exam, they're very useful. Okay, immediately looking at this, I'm seeing that, okay, this is following, when x is very small, it's following quite close to a diagonal line. So I would suggest y equals x, and look at that, it's quite close when x is small. Looking at the other options, you have y is equal to 1 plus x, which doesn't even touch the curve, so that's not a good sign. You've got y is equal to 1, which is only good because it intersects at one point on the curve, but not near 0, and y is equal to 0, which again isn't so good and doesn't really come tangent anywhere. So we're doing y is equal to x. Again, visually, this will help. Okay, if you look at it visually, it's much easier to see. Okay, moving on. We have not done Maclaurin series yet, so I will not get into that. However, it is C in this case. Thankfully, there's no real range of values for which an expansion is valid. And 10 and 11, I expect you guys to get. So tan of 3, bloody... Yeah, so you guys can just input this on your calculator. Tan of 3 pi over 4 is simply just going to be -1, I believe. -1? Let me check. Always put your bloody thing in radians. I cannot tell you how many times I have suffered because I have forgotten to put something in radians. It is -1, so it's fairly easy. I don't expect anyone to really get that wrong. And the derivative of cos, again, very easy thing here. Derivative of cos is just going to be minus sign in this case. So, yeah. So cos x, just minus sign. Okay. That, I think, is most of it already done. We have not done this kind of form here. This is a modulus argument form of complex numbers. I don't think anyone's done this yet, so just hold off on that. This is Euler's theorem or equation, which again you have not done. This one you can do. All right. So for 14, you get you've got dy dt plus 6y equals 24e2t. Now there is a way of doing this called the integrating factor method, which I believe I mentioned the page number of in here somewhere. Yep, page 515 shows this method quite well. All right, so look at that. Oh wait, come on now. All right, so what we're going to do is we're going to take this coefficient of the y here, and we're going to essentially integrate it with respect to t, so we get 6t. Therefore, we're going to get a value e6t, and we're going to multiply that by the entire thing. So we get e6t plus 6y e6t, and then you have 24e8t, because we've added the 2t and the 6t together. Then we phrase it as y times e6t, all right? Because this is functionally similar. This is essentially product rule being represented here, and essentially just going back on ourselves just allows us to sort of do it, to bring it back up. And then we can integrate this side. So we have 24e8t dt, and integrating this should be fairly simple. It's 3e8t. So you have something like that. Hold on. So you have what? Yeah, so hold on, sorry. Yeah, you have 6e8t plus c. And simply put, because we have the e6t on the other side, we're just going to divide by e6t, and we get 3e2t, which is c, and I believe that's correct. 14c? Yes, 14 is c. Okay, hopefully that's clear enough. 15 we haven't done yet, so don't worry about it. 16 is a second-order homogeneous differential equation, which we have not done yet. This is a further difference equation. Again, we haven't done yet. Eigenvalues we haven't done. Characteristic polynomial we haven't done. Eigenvalues we haven't done. Characteristic polynomial, eigenvalues, complex eigenvalues. Again, you have, a fixed point at the origin for a differential equation system AX is, yeah, again, we haven't done stable nodes and stuff like that. And eigenvalues again. So that's the end of it then. That was pretty short, mostly because there's not many questions in this that do apply. But there are questions that do apply. So I just wanted to let you guys know that that's them and that's the solutions. Okay, I should be done now. Have a lovely evening, whatever you guys are doing, and good luck with the exam tomorrow. Okay, bye.